risk assessment. Our quiz for kinetics and mass balance is going to be next week on Wednesday. So problems are going to be due before the class starts. And if you have questions, please remember, come and talk to me during office hours. If you have some problems with the solved problems or any other thing that might come up from studying. Before we start mass balance, I mentioned that I was gonna give you time to ask me questions about reading notes. Did you guys have time to go and check them out and the format? And is there any question?
I have a question, Professor.
Yes.
So I noticed that it says on there that it's only one side, but then when I was reading further into it, it looked like one side should be only conversion factors and another side should be formulas. So I wasn't,
Yes.
I didn't understand if it's actually one-sided or is it actually double-sided?
Yeah, thank you for that question. So the reading notes, the theory is one side. However, in the chapters coming, there's going to be formulas, conversions factors, and definitions for the terms in the formula. So you can use the back of the page for those things. But the theory, the definitions, all of that is going to be only one side of the page.
All right, thank you.
Yeah. And I hope that it makes sense what's the difference. The reading notes are not formulas. Formulas are formulas, right? Equation sheets. The reading notes is actually theory definitions that you can put on that page. And remember, these notes can be used in the quiz, and they're going to be submitted with your quiz. So when you prepare them, if you prepare them electronically, it's going to be easier for you to submit them. If you prepare those by hand, make sure that you scan it in advance on the quiz because you need to submit them with the quiz. And those are the ones that you're going to be using for the final exam or the midterm too. Okay?
Wait, I had a quick question. So I'm like looking at the instructions. So it says like on one side, it's the content side. And it says only include definitions and conversion factors. So do we not include like concepts or, as you said, like theories?
Definition and theory.
Okay, so we could include theories. It doesn't only have to be definitions.
Theory, yes.
Okay.
Definitions, theory.
Okay, thank you.
It's what I would call the things that students don't want to memorize on time. The definition of alkalinity, for example, right, is the capacity to buffer the pH change of the water. So there's going to be some things that maybe you want to have the definitions in there. From your reading, you will see, and you can do some summary too of the content of the chapter. So look at the guidelines. It tells you how to start reading the chapter, how to approach the different topics, the content. It's not a transcription of everything. You won't have the time to actually do that. It's more like a summary of what you are reading and what it means. Any other question?
The notes we can use on like a quiz or stuff, they said there's like, they could be like definitions or just formulas.
In one side, only definitions and theory. On the back of the page is formulas or conversion factors.
Okay.
The typical equation sheet that you will prepare for an exam.
Got it.
Does that make sense? If someone gets done with it, feel free to come to my office hour, take a photo if you're doing it by hand and show it to me. If you are moving along and you're not sure, come and check with me during office hours. More than happy to look at it to help you if you have any question, right? And in none of the sites, problem solved or steps to solve problems, because not all the problems are going to be requiring steps. And then with problem solvers, you're just going to get distracted trying to solve the problem the same way. So I would not advise you to do that. Okay.
Professor, sorry, just one more question. So the reading notes are for the chapter, right? So we read the chapter and we take notes from that?
Yeah, for the topic. So we cover risk management and assessment. That's one topic. Later we'll talk about solids. That's going to be another page, right? Reading notes. And then we'll talk about water quality, and there will be another page of reading notes.
Okay, but it will be pretty much just reading from the book. Is that correct?
Yes.
Okay, thank you.
Yeah, the book has a lot of very good information, too much information, and I think that is important that we take the time to read some of those things to make sure that when I talked about them in class, everybody knows, it's on the same page. Unfortunately, the time in the class is limited, so we don't have too much time to talk about everything. So that will help you when you come in here and maybe you already have a question, and when I'm talking about that topic, then you can bring up the question, or maybe I explain or cover it when we're talking about it. But it's gonna be easier like that. Okay, so remember, these notes are going to be giving you a credit on the quiz, so you need to submit them when you have your quiz. Okay, there's gonna be a question for you to submit it. And I don't understand the question that the book doesn't contain a summary on the chapters. No, you're gonna be doing the summary. How you're gonna be? What are you supposed to do? You're gonna be looking at the summary. You're gonna be doing the summary. Your reading notes are the summary for you.
I like doing that too, reading the summary at the end of the chapter, but there isn't a summary at the end of the chapters in this book.
So my notes say that it's a summary at the end?
Your notes say to begin our like our process by reading the summary at the end of each chapter and then going through the outlines for the bold font in the chapter, but there is no summary.
Okay, so then maybe it's my mistake. Maybe for my other class, then I'm sorry, I apologize. There is no summary. Thank you for catching that, Matt. Matt, is it Matt or Matthew?
Either one.
Okay, so yes, I apologize. There is no summary at the end of the chapter. The notes are the summary. You need to do the summary. Okay, good point. I'll edit that, and I'll make sure that it's accurate. Alrighty. So, any other question about reading notes? And if you don't have a question right now and you have questions, please come to see me during office hours today. A couple of people came to ask questions about it. Well, you know where to find me. Emails are harder because I teach. I'm all day long on Zoom. I don't have the opportunity to check my emails as I used to do before. So it might take way longer to get back to you. And some of you have sent me emails a few weeks ago. I mean, I'm responding, but still it's gonna take time. So if it's timely, please come to office hours. That will be the most effective way. So reading notes. Now let me talk about the project quickly. I don't know if you noticed, but I have checked every single submission, the different teams related to the project proposal. I made comments about format in general, suggesting you to change, to add, to remove, and also the most common, I don't want to say an issue, but the most common topic right now is, I think that the scope of the project is too huge. Look at the proposal. The proposal is, or the COFO proposal is asking you that you need to do something in the no exceeding $20,000 plus or minus 5,000 or some 5,000, 2,000, something like that. This is not an engineering real proposal. This will be more in the size of a student project, a proof of concept that may be based on the results that you think, the analysis that you can do, you scale it up. Then you can say we can help the campus meeting the goal and UN goals, etc. So please keep that in mind, because otherwise the project is going to be huge. The idea is not to have a real engineering proposal. It's an engineering proposal but to the scale of a pilot. And because of the budget, you can't tell that. So if you have any questions, or maybe I got confused with the idea, it's okay too. It's just a preliminary idea. I'm very happy that everybody has a very defined scope, and you have identified the sources where you're going to be getting some data. Now, talking about the data, there is one proposal, but three of the proposals are kind of, the one proposal very specifically saying, we're going to go to campus, we're going to interview people, I just want to make sure that everybody has clear we are not going to campus. The intent of the project is not sending you to campus. The campus is closed. Nobody's allowed to go to campus. So please don't go to campus. Let's do whatever we can with the data that you can find online. And if you cannot find anything specific to Cal Poly from the cases that you show me that you have identified, you can get data and try to extrapolate this similar community, or just we couldn't find data and we're going to be assuming that it's the same. And it's okay. It's just an exercise, an academic exercise where you're going to be using the tools to calculate carbon footprinting and then look into savings and operation and maintenance, etc. for that little pilot study. So please, no going to campus. That's very important for our own health, and until the campus authorities say otherwise. Okay, so you're gonna make sure that you haven't understood that you need to go to campus. No, it's just an academic project, and you can work with any data that you find. All right. With that, let's start and finish mass balance first, and then we'll move on to the next topic. So I'm gonna be sharing my iPad now. And in here we have this problem. We're gonna try to work all together in the problem. We have a well-mixed lagoon, sewage lagoon, and it's a shallow pond. That's the definition of a lagoon, if you don't know what a lagoon is. And it's receiving a 430 cubic meters per day of untreated sewage. The lagoon has a surface area of 10 hectares and a depth of 1 meter. The pollutant has a concentration of 180 milligrams per liter. The organic matter in the sewage degrades biologically, and according to the first order reaction. The reaction rate constant is 0.71/day. Assuming that no other losses or gains like evaporation or rainfall are taking place, and we assume that the lagoon is completely mixed, and we need to find the steady state concentration of the pollutant in the lagoon effluent. So we need to start doing this problem. If we look at the steps of mass balance, the mass balance is, the first step is going to be telling us that we need to define our boundaries so we can have our free body diagram, or diagram that is very simple, that is going to be very easy to know what's happening. So I have a question for you. Do you see what's happening here? Can you tell what's going on in the problem? Anyone? But we have a sewage lagoon. How do they look like? I don't know, maybe a square, maybe circular. So I'm just gonna model my system as a circular tank or pit. And it says that we have discharging 430 cubic meters per day. And this is untreated sewage at a concentration of, let's put it here, S for sewage, a concentration of 180 milligrams per liter. We know the surface area is 10 hectares. It tells us about the depth is 1 meter. And then something is happening in there. The sewage is being degraded. And we have a rate constant of 0.71/day. There is no gains or losses. We need to find the steady state concentration of the lagoon in the effluent. So the effluent is the line that is going to be exiting. And we need to find the steady state concentration of the lagoon. Do we know the flow rate that goes out?
It should be equal to QN.
E should be equal to QE because there is, according to the statement, there is no other input or output, is it? So if no other input or output, in this case, Q in is equals to Q out, or QS is equals to QF. If the system has another input or output, then it will be the sum of either the inputs or the sum of the outputs, and that will be a different problem. And you have a few problems on the practice problems. There's different type of problems for you to look into. So we have one line coming in or inlet and one out. To make this simpler, we can just have this diagram representing this, always remembering that we're going to have a reaction rate happening. So if we do the boundaries of our system, they're going to be within that red line. And let's put in here the 0.71 over there just to make sure that we don't forget that there is a reaction happening in there. According to the statement, what happens to the pollutant? Is it forming or disappearing?
Disappearing.
Disappearing. So the sign is going to be?
Negative.
It's going to be negative. So this is going to be a decay reaction or negative sign. Let's label in here. We have QS equals to, it's repetitive, but let's put it all together in our diagram, and we're going to be doing the setting of the mass balance equation right here. So now I know QF length based on what I just put in there, they are the same. The F length is going to be equals to 430 cubic meters per day. And I'm looking the F length concentration. I know some of you are going to try to jump into the solution. This is a very simple problem. If we just jump into the solution, it might be easier. Let's set up all the equations and make sure that you follow this process when you're doing your practice problems. So let's look at the words. With words, the equation of mass balance is going to be accumulation equals in minus out, plus or minus the generation term. Are we working under steady state?
Yes.
Yes. The statement this time says clearly steady state. However, if it doesn't say, and we don't see time given anywhere, and if we see time given somewhere, we'll be very cautious and let's look at the time, maybe just for tricking me, or maybe just given extra, right? But in this case, there is no time. It says a steady state, so this is going to be equals to 0. Do we have a generation term? The generation term has many different images depending on what? Or forms. This is kinetics.
The reaction order and type of reaction.
The reaction order. Thank you so much, Brock. So the reaction order. What kind of reaction order do we have in here?
First order. Yeah.
So we have a first order. And if it is a first order and the type of the reaction is?
Decay.
Decay. What is the form of my term, Jen?
Is it negative?
It's negative. And then what terms do they go there?
VKC.
VKC. Perfect. And if some of you are wondering where are they getting this from, these are the notes from kinetics. First order decay, they give you that form for the generation term. So we already know that term. Now let's put it all together. So accumulation is equals to 0. In is going to be multiplying. And remember, in and out are going to be in what units? Overall from this term, what units are we expecting to have?
Mass time.
Mass time. Thank you so much. So to have mass time, we need to have QS coming in, CS coming in minus Q F1, C F1 minus VKC. I am looking for the CF. I know QS, I know CS, I know QF. I know K. Do I know volume?
Yes.
Yes. Oh, what about C? What is this C? Where should I place it on my system? C where? Look at the drawing.
Would it be C inside?
C inside, perfect. So this is C inside. So C inside. Per the assumptions of a completely mixed flow rate reactor, what is the relationship between the C inside and the C effluent?
It's the same as the C outside.
It's the same as the C outside, so they are the same, right? So C inside, C effluent is going to be equals to C inside, and I don't have two variables. I just have one variable, and we're going to put them together and solve the problem. So if we solve this, my C effluent, and probably this equation is going to be familiar for you, C effluent is equals to the CS QS divided by Q effluent plus KB. And we know everything. CS is 180 milligrams per liter times the flow rate, which is 430 cubic meters per day. Let's see, we need to add some conversion factors in there. And then we're going to be multiplying or converting into liters. So we need to have the 1,000 liters divided by cubic meter, and then divided by 430 cubic meters per day times 1,000 plus K, which is 0.7 over day, and the volume we need to convert in here is going to be hectares, but when we're looking into meters all over the place. So put in here, it was 10. The statement says that is 10 hectares, right? Yes. 10 hectares times 1 meter. And how many, can we convert that into meters? How many meters, square meters in a hectare?
It's 10,000. I looked it up. I didn't know that.
Okay, thank you so much. Yeah, you can look it up. Right now, we need to take advantage of technology, right? If I'm asking you here, like conversion factor, if we don't know it, let's look it up. It's fine. So you said 10,000. Yeah, 10 to the 4 square meters. So when you do this whole equation, can we look at the volume here in cubic meters? If it is 10,000, well, it's going to be 10,000 cubic meters. And then 10,000 cubic meters, but then we need to multiply times 1,000 liters per cubic meter, right? So what would you get for the effluent concentration? Do the whole calculation in there.
I'm confused actually on something.
Okay.
It says the 10 hectare, that's 10 hectares, but then it said 1 hectare is 10,000. So wouldn't that be like 10 times 10,000?
10,000 square meters, isn't it?
Yeah. No, it's because you wrote like...
Yes, yeah. I see what you're saying.
Okay, thank you.
So it's times 10 because it's 1 and we have 10, right? So here on the equation, I'm just missing 1 0. There you go. Thank you for that. Is that correct? 100,000. Yeah, that should be correct. 100,000. It's yes or not? Am I missing something else? What is the number here, David?
Oh, it should be 100,000.
The volume?
Yeah.
Okay. All right, let's have the board clear. So what do you get for the concentration?
Aren't we working with liters and meters cubed?
We are, if you notice in here, let me put in pink.
Is that 1,000 at the end? Is that
cubic meters? Is removed.
Okay.
Right? And here, well, let's double check the question. In here, we get rid of the cubic meters. And in here, the cubic meters I multiply times 1,000 to remove the cubic meters. So we're working on liters. Does that make sense? I think it's easier to do the dimensional analysis like that, just to make sure that it's accurate.
I don't know if I got 1.1.
1.1. Okay, and the units are milligrams per liter of concentration. Can someone check the number? I'm getting different numbers on the chat, so I need someone else to check. I got two different numbers on the chat.
So I could second that 1.1.
Okay, so someone is second the 1.1, and the numbers on the chart are totally different. So consensus here. So my advice is to approach the mass balance problems like this. Set up the whole mass balance equation, and I'm going to tell you where is a common mistake for everybody. In the exam, I have seen that students jump immediately into solving for different terms rather than setting up the equation. And the big mistake falls here. When you set up the equation for the sign for the, in this case, decay, for the generation term, when you're solving for this, you move it on to the other side of the equation and goes positive. But as soon as solve it as a negative, even though it's already solving for CF, for example, they will put a negative right here. So my advice is set up your mass balance equation, set up the sign of the generation term in there, and then solve for whatever term you need to solve for to ensure that you don't get confused with the change of sign due to this solving for a given variable that you're looking for.
Professor, I had a question. Could you please explain where you found the volume one more time, please? I'm kind of confused in that area.
Oh yeah, sure. The volume, we were given the area in hectares and the depth. So what we did in here is just 10 hectares times 1 meter. And on the bottom there, given the conversion factor that Matt provided, the volume is equals 100,000 cubic meters, and then just convert it to liters with this conversion factor.
Okay, thank you.
Okay, okie dokie. So I'm gonna make any question about this problem? So far, so good? So I need to talk about the way the books many times get confusing when they talk about mass balance and how the system efficiency is defined and how the concentration can be changing. So I'm going to be changing the page. Okay. This is no problem number 3. Actually, we can. So in mass balance, a problem can tell you about efficiency of system. What is the system? The system is that, in this case, like the lagoon that we are studying. So let me just bring up the lagoon, for example, right? For example, what system? The lagoon. And this is the system or the process that we were studying. This is the system, okay? Whatever you're studying or you're conducting mass balance around, that is your system. So the efficiency of the system refers to the mass per time change. Okay, so what does that mean? If, for example, the lagoon is 60% efficient, that means that the mass per time that is coming in is going to be, think about this is environmental engineering. We're treating the waste. 60% is being removed. 60% is removed. 60% is removed. 60% of what? 60% of the pollutant. In this case was sewage. So we are talking about the mass per day or kilograms per day or pounds per day that are entering. 60% of those are removed, and then the 40% remaining will be going into the effluent. And let me put it complete in here. 40% of pollutant, the pounds per day or the kilograms per day, 40% of the mass rate, example, kilograms per day or pounds per day. I'm gonna remove this to make sure that it's clear. Exit the system. In environmental engineering and water treatment, the removal efficiency is the cleaning efficiency of our system. And it's going to be referring to the mass rate. Okay, when we talk about removal efficiency, it's talking about mass rate. There is another type of wording that I want to contrast just to make sure that you don't get confused. If we're talking about concentration, as an example, I'm going to use the same lagoon, okay? It's going to be a completely different problem, but we're using the same lagoon. If I say that the concentration is, I'm going to change the number so you don't think that this is the same problem that we just solved. This is just an example. It's 30 milligrams per liter. And the statement says concentration is reduced by 90%. In this situation, the wording is very specific and says that the concentration is reduced, not that the mass rate. It's not talking about the efficiency of the system. It's talking about the concentration that is coming in. So if that is the case, the concentration is reduced in the system and we have an effluent, is going to be, what is going to be equals to? 90%?
10%?
10%.
3 milligrams per liter.
Okay, so you already did the calculation, 3 milligrams per liter, but let me put it specifically here, 10% of the initial concentration, that in this case is going to be 0.1 times 30 or 3 milligrams per liter, right? So I just want to make sure that there is a clear difference in the wording. The problem can tell you about the efficiency of the system. And if it was efficiency of the system, and you have Q and you have S, what you need to do is multiply Q times CS times, here is the 100% coming in. But if we go to the effluent, it could be QS times CS times what? What percent of the mass per time is leaving the system?
0.1.
Matt, can we use the number that we have on the example?
Oh, so it would be 40%.
40% or 0.4. Yes. I want to make sure that I don't use the numbers on the example. They're two independent examples. All right? Does that make sense? Does that make sense? So we talk about efficiency of the system. We're talking about the flow and the mass that come together. But sometimes the statement is very clear, is the concentration. And I have seen the students getting confused confused and interchanging them, and it is not the same. So
what gets interchanged?
The what?
What gets interchanged or like confused?
Oh, for example, the statement tells you the efficiency of the system is 60% removal, and a student will come and say, oh, the concentration coming in is 30%, so I'm just going to multiply by 0.4, and that is the effluent concentration. So some of you are thinking this, well, in this problem, that is actually true. Yes, only in this situation. The moment that we have another incoming line or another outlet, it is not going to be true. Okay? So always read the statement. And if it is regarding efficiency, this is the keyword of system, then it's going to be mass rate. And if it is just concentration reduce or increase, then it's going to be a percent of the concentration. Okay? But this is very important. Always keep this in mind, because always the efficiency of the system is confused by, oh, the concentration is 30, then I have to just reduce by the efficiency. No. If it is efficiency, is the whole thing, and the whole thing is going to be treating the water and the concentration together. All right. Okay. Any questions? No questions? So far, so good? Okay. So we are going to finish with this mass balance. Please go and check the problems, the practice problems. There is, I believe, 3 or 4. I was checking them yesterday, but I forgot the number. 3 or 4. Some of them are for the step function, and some of them are for mass balance in general to practice. Do your boundary conditions, make sure that you define your system really well to see what's going in and what's going out. Set up your equations, and if there's any question, please come and let me know. All right. So now we are going to start the risk assessment and management.
Hey, Dr. Palomo, where
Yes.
can we submit the reading notes for risk assessment?
The risk assessment notes are going to be submitted with your quiz. All right, so they're not going to be due on Blackboard or anything anytime soon. They are due when you, when the moment that you do your quiz, just submit them in there, get them ready to be submitted.
Okay. Is it going to be the risk assessment quiz or the mass balance quiz?
Yeah, the risk assessment.
Okay, thank you.
Yeah, remember they're due when you're looking at the quiz, when you are needing them. All right. So technically, you have a lot of time to get them done, right? Until we have the quiz. Ideally, you wanna at least read a little bit of the chapter, scan through it, and see what topics are there, and based on that, do your notes. So I won't be able to cover all the things on the chapter. It's a lot of information, really good information, but unfortunately, we don't have the time to talk about all of those. And it's very good information. All right. And yes, you are gonna still getting credit for submitting your class notes. Right? The class notes are going to be mainly problem solved and minimum notes. I'm gonna reduce significantly the amount of information that I'm gonna be putting on the whiteboard, and I'm gonna be trying to concentrate more on problem solution. Okay? Okie dokie. Oh, actually, hold on. This is so this is our risk assessment and management. See, I put my PowerPoint in here. to try to reduce the movement between laptop and iPad. Hopefully will be smoother. Well, let's talk about the learning objectives. We are going to introduce a new topic. It's very interesting. Last time that I was talking about this topic is when the pandemic was about to start. I think that was 2 weeks before we were sent into lockdown or stay home order. And now we are in the middle of the pandemic, and we're going to be talking about hazards and risk assessment and risk management. So we're going to have a very good example to talk about this topic. And we're going to it, and we're going to understand the significance. But to talk about this, I'm not only going to be using COVID, I'm going to use other things that are very, you see daily, and you saw before COVID, just to make sure that it's clear. However, our topic is going to be guided towards the protection of human health due to the exposure to environmental contaminants. So I'm going to give you some examples that might not be really related to environmental or pollutants, but they still are significant. So we're going to talk about hazards and the risk. How do we assess? I'm going to be giving you very specific equations that you need to use. We need to learn how to use some tables that are used for risk assessment that we do not develop. We need to know how to use them. Epidemiologists are the ones that are going to be developing these type of tables for us. And then you're going to be learning about routes of exposure, and you need to determine which one is of more concern, and probably we all are already familiar with that a little bit due to the pandemic, and we need to talk about or probably review some of the terms like chronic and acute. And then the most important thing is going to be talking about CDI and HI, which are the two parameters to actually measure the risk or determine the risk of exposure from two different chemicals or contaminants. Okay. So what we're going to be doing is talk about risk assessment and management. And this is the chapter 4 in your textbook. So when we talk about risk assessment, we need to talk about different technical information. Technical information is usually what we are going to be handling if we are acting as engineers or scientists. If you are in policy development, probably you're going to be more into the management side. The class is going to be concentrated more into the risk assessment, assessing what is the risk if we do this or we don't do something else. Also, we need to take into account the financial information. What is the cost to have vaccines for everybody? Or what is the cost of not wearing a mask? Or what is the cost of doing this or not doing that? With that, we can determine the level of risk. And we will talk about how the risk can be perceived, can be voluntary, can be involuntary, and talk about some of those examples. And then decision making. So engineers need technical information, financial information, and then knowing the level of risk, we can decide what to do. But individually too, we are always going through that process, even if we don't realize that we go through that process. So assessment. Assessment is going to be concentrated. So specifically, if you ask me, what do you mean assessment and management? What is the difference? Assessment is gathering of the scientific data, all the facts. All the data is gathered, is interpreted from the point of view of a scientist, right? The facts. These are facts. And if we want to talk about in terms of the language of risk and assessment, it will be those response curves, and we'll talk about what they are or how they look like. And other information related to it. Now, what is risk management? Management is going to be more about decision making, what to do. What to do. Why? Well, but it's uncertain. There is uncertainty here. Some of you are going to be thinking, well, that's a number. Is it really going to happen? And you have seen that right now with COVID-19. Some people say, no, the mask doesn't work. No, it works. 6 feet, 20 feet is the same or not. So there is uncertainty. And we need to make decisions. Someone was telling me, a civil engineer, a retired lieutenant from the Army, I have seen 1 meter apart and I have seen 6 feet apart. If you convert the units, they are not the same. Which one is right? He's a structural engineer. He comes and asks me that. So there is an uncertainty in there. Sometimes we go plus or minus and we round up or round down. And that uncertainty here is going to be falling on the manager or the one that is going to be deciding on what is going to be the information putting on that publication or handout or flyer that is going to be sent out to the public saying 1 meter or 6 feet apart, or maybe the state decides what it is. So there is uncertainty, and the authorities are going to be making that decision. Also, it's allocating resources. They need to decide if it is very expensive or the expense is justified regardless of the cost. So it could be a local expense, right, or local resource, or it could be a state, or it could be federal. For example, for the fires, the allocation of the resources for fires could come from all the different levels of funding, local, state, or federal. And whoever is making the decision is going to be deciding why and justifying that too. And we don't have fires. I mean, we do have fires every year, but they're not always the same. Some of years, like this year, is really bad. Nobody knows how bad it's going to be, and they don't prepare for the worst to give the budget. They find a way to predict what is the probability or the risk to have a given size of fire, and decisions come from there. So everything is risky, everything. Is that true? What do you think?
I think there is a certain level of risk in everything.
There is a level of risk on everything. If we like to drive motorcycles, just getting on the freeway is a huge risk. Drinking water from the tap is a risk. Drinking bottled water is a risk because you don't know what's in there. You just believe that whatever they're selling to you is good, right? There is no way to go and tell what's on the water. If there's going to be someone careless driving today on the freeway, so you just take the risk. So let me go here, and everything is risky, and I can show you here. And let's understand, this is very important. When we talk about risk, we are always talking about the health of people and the life of people. In environmental engineering, we're going to be going to the bottom line. If there is what is the risk in terms of keeping people safe? And it's going to be translated many times into lethal doses. So here we're looking into the causes of death. And yes, it's not very current. This table is a little bit old, however, still relevant to illustrate or the principles in the class. So cancer, annual deaths, it's whatever number, let's concentrate on the percent right now, 24%. I believe because of detection, it could have been going higher, but the numbers are always, the percentage stays steady. Motorcycle accidents, that probably is not gonna change. I don't see more people driving motorcycles because we have more traffic. Other causes of death are there too, and it might be 1.2%. So overall, everything is risky. Even if we just have a flu, it could be fatal if we don't have a good health, we don't do exercise, etc. So the way that we live is always going to be talking about the chances for fatality. So we talk about risk. Very important, risk has no units. No units. It's just going to be a number. It's a number associated to a given activity. It is a number associated to an activity, and we just look at the different activities, right? So I'm going to be showing you another table here. We're looking at the risk of death, annual risk of death for different activities and per 100,000 people. So risk is going to be in reference to a number of people. In this case, the table says 100,000 people. We have risk of death with motorcycles. It is right here, 2,000 in 100,000 people. Farming still is risky, right? What is the risk of farming, of death from farming? How many people out of 100,000?
36.
36. Oh, peanut butter? How many of you like peanut butter? You don't have to tell me. There is a risk of a fatality from peanut butter because, and it's a 0.8 annually in 100,000 people. The aflatoxin it's a substance that naturally happens in peanuts, and it's toxic for you. Yeah, some of you are sad, I know, but look at this, is 40 tablespoons, right, per day. So hopefully you're not there. And actually there is a series related to the peanut butter and the toxicity, and it's not good for humans, and we are allergic to it, and blah, blah, blah. So naturally your body knows that it's not good for us. Some of us have heavy or very bad allergies from peanut butter, probably because of this toxin. So now we know the reason why. How many of you love the 4th of July steaks out there? Or yeah, this is about steaks, charcoal broiled steaks. I do. I love it. I don't think I want to change it. I'm sorry. Still, there is a chance of death by this because of the PAH, the polyaromatic hydrocarbons, which are carcinogens. So I am personally okay with the risk of dying for this. I don't need it every day though. But with time, and we're going to talk about chronic, with time, there could be an effect on your health because of the exposure. So the last one that I want to talk about is the one that we're going to be talking about when we talk about environmental exposure, which is 1 in a million lifetime risk. And 1 in a million lifetime risk is the one that EPA is going to be using to assess if something is, if we want to take the risk or not. So the limit per se. 1 times 10 to the minus 6 is going to be the risk that should not be exceeded if we're exposed to contaminants. And that is the one by the EPA. And I'll now show you this in here. But let me talk about this mortality. We're talking about mortality and 1 in a million. What activities could be leading to mortality or it's risky, right? We do those activities like me eating the steak because I really like the steak. Well, if someone smokes, then it's a chance for a risk for cancer. So it might not be lethal in this case, but cancer could lead to death. They could be drinking wine. Who would have said that? I have read many articles that wine is good for you, and now I hear that there is a chance of cirrhosis on the liver. So everything that we do can lead to something that could be negative for your health. It could be acute if it is a lot, it could be chronic with time. We need to have a conscious decision of what we are doing. Traveling 300 miles by car or flying by jet, or living in Denver. What if you got for an internship in Denver because it's higher up versus compared to the sea level, you are closer to the sunlight or the UV rays are hitting you harder. So cosmic radiation could cause cancer. Everything that we do in life has a risk or could have a consequence here. Even living near a radioactive or nuclear reactor could be a risk. I don't even know where the reactors are. I don't want to know. No, we know where they are. Hopefully you know where they are. Hopefully you will be deciding if you want to continue living near a nuclear reactor. We have few of those in US. So again, what am I showing you this? I'm just want to make the point that there are risks in life. Everything that we do is going to have a risk, and even living in LA. So in here on the example, they talk about Boston and New York, but we can also add in here LA. Should I smile or sad? Probably sad. Now we have the fires, right? LA has to be added in there for the air pollution. So just by making the decision of living in here, we are increasing our risk of getting sick due to the air pollution. Now, we also talk about looking into the information, the facts, and then decide the resource allocation. So sometimes resource allocation is going to be something that is going to help us to look into, should we do something before it happens, or should we just pay the price? Like immunizations is direct savings because it's done before anything. We don't want anybody to get sick, right? Just better do immunizations. Or like eliminating the lead from the gas. If you reduce the level of lead in the gas, you are not going to be remediating the lead that is spread in the environment, the soil, mainly soil and groundwater, and etc. It goes like that, but in some cases, there is a big cost, and some of the decision makers are hesitant about providing them. And I don't know. I know that you're going to be voting, and this is coming here, dialysis centers. Make sure when you, please vote, and make sure that you read very well about those propositions, and you vote for whatever you think will be the best for the population in California and for the well-being of everybody. Alrighty, so we got here to EPA. EPA is going to regulates. EPA regulates the exposure to toxic levels of chemicals, okay? And we care about the risk not to exceed 1 times 10 to the minus 6. So our target risk is 1 times 10 to the minus 6. This is the regulation. Risk should not exceed this number. So the actual risk should not exceed the 1 times 10 to the minus 6. So as you can tell, we're going to be looking at very, very, very tiny values. Is there any questions so far? No? Okay. So let me let's do this. I want you to, I'm going to stop sharing with the iPad. I haven't told you how to calculate the risk. The only thing that you know is 1 times 10 to the minus 6. What does that mean? Is 1 over a million. Okay, so let's do this. Can we do a quick search? And actually, we're going to be doing this. We're going to go into breakout rooms. You're going to have only 5 minutes. What you're doing is finding in California or maybe United States or maybe a different state, I want you to find the number, what is the risk, the reported value of getting sick with COVID-19. Okay, go online, look as much as you can, and you need to find a number, maybe 30 in 100,000 or 50, whatever is the ratio. I haven't seen the value in yes in the 1 to the minus 6 or 5 to in a million, but maybe you can find it. So everybody understand what you need to do together as a group. You're going to be finding what is the risk of getting COVID-19, not of dying, of getting sick. Yes? Thumbs up.
Is it the risk per like county we live in or state?
Whatever you can find, baby. It could be county, it can be in US. So if you find different numbers, it's gonna be fine. So I'm gonna be sending you out in breakout rooms.
Hey guys.
Hey.
Did you guys find anything?
I'm looking for Florida right now, or I'm looking at Florida right now.
Okay. It's kind of hard to find like a specific number. It seems like it's more directed to like the activity you do compared to rather, you know, where you live.
I found a data that said that it's like if you go to like an event in Florida with like 10 people, there is a chance that you can get COVID, like 35% chance. And then 25 people, 71% chance. But I don't know if that's what she wants.
I think that sounds pretty good to what, like, I would imagine that is what she's looking for.
Yeah.
I just can't really find anything for California.
True.
It just says like this activity increases your risk and this activity doesn't, but it doesn't give me any specific numbers. How did you search for it?
Oh, I just put risk of COVID-19 in Florida, and then I went through like a bunch of links, and then whatever said like percentage, I'm like, okay.
I did the same, but in California, and I can't find anything.
Yeah. Yeah, it's kind of hard to find like percentage wise.
If I see like 1 in like 10,000 per county.
Oh whoa.
That's what you found?
Yeah, I just sent it on the text to the group. I don't know how to send photos on this.
Okay.
Alright. I just dropped the link in the Discord for information on the LA County one.
Oh, perfect. Thank you.
Yeah, just give cases, and then if you go to the bottom, the asterisks give it. The case numbers are in cases per 100,000 residents. So I think that's what she's looking for, really.
Yeah.
I think as long as we have numbers, I think we're good.
Yeah.
Yeah. Whatever.
Yeah, all I'm finding is like the death rate. Sorry, I was kind of looking. I didn't mean to be quiet about it.
No, you're good. Don't worry.
Yeah, that's pretty good.
Yeah, I just want this COVID to be over.
I know, right?
Like, it's been going for like 9 months already.
It's been way too long. I was thinking that, once it started, I was thinking that it would be over in like a month, and then we can go back to living our normal life.
True.
I was really just hoping that we would lose the summer and that would be it.
Yeah, me too. That's what I thought too. Or like spring break, and that's about it. But which one do you guys want to share? Like, who information do you guys want to share? Just in case she asks us.
Should we do Pomona? You guys want to do the city of Pomona?
Yeah, we can do Pomona.
That's where school is.
Sounds good to me.
Which group are we?
3.
Okay. I always forget.
Okay. It was quick. Were you able to find it? Can you give me thumbs up? All right. Who wants to share? What did you find, Maria?
Well, our group found that in the city of Pomona, per every 100,000 people, the risk of getting coronavirus is 3,734.
So can you repeat again? It's 3,000?
Yes, 3,734.
Per 10,000?
Per 100,000, I think.
Okay.
Yeah, 100,000. Yeah.
If you divide that, the 3,700 by 100,000, what is the fraction that you have left?
That's 0.037.
0.03. If you compare that to 1 times 10 to the minus 6, is it smaller?
No, it's much bigger.
It's much bigger. So it's really risky, right, for your health. All right. Someone else? I don't remember who was giving me thumbs up.
Our group looked up in California as a whole. We found 0.0219.
0.0219. Okay, compared to 1 times 10 to the minus 6?
It's a lot bigger as well.
A lot bigger. Compared to Pomona only, which one is bigger?
Pomona.
Pomona, why would that be? That's another reason. We can talk about the reasons later. Can't go into political issues. All right. Anyone else that wants to share your number? Come on, one more.
We looked at the nationwide, and it was 2.37% has caught the virus in the United States.
So you found it as a percent, 2.37, right?
Yes, and the percent that died from COVID is 0.00065%.
So dying is less probable than getting sick. And so sometimes risk can be approximated as a percent too. So how do you get the fraction? If you get a fraction, 2% will be 0.02, right? And if you compare that to the 1 times 10 to the minus 6, it's 1/50. So it's way, way larger than 1 times 10 to the minus 6. So you don't even know how to calculate the risk yet, but you know what the risk is. You have found it, you have seen it, and we are going to learn how to calculate risks in here. We're going to concentrate on how to do it for exposure to chemicals that are present in water or from chemicals that are on the air. And now, congratulations, you know what the risk is, you know how to find it, and now we're going to learn how to calculate it. So to be able to do that, we just let's finish here. I'm going to share my iPad again to finish this portion of the theory and then be able to go and do some problems. When we talk about risk, it has to be a balance between what is acceptable. So if you were little and you used to go to the playground, right? You know what I'm talking about, balancing. And I was always a very short person, even when I was little. And all my friends were very, very tall. So we always needed to find a way to balance that. And similar to that is the funding that takes to take care of a risk and what is an acceptable risk. So we have been all over life trying to find a balance in different aspects. In this case, it's risk. How much risk is acceptable? And then EPA, obviously, EPA says 1 times 10 to the minus 6 or less is acceptable. Okay? So if we talk about a standard or a value that is going to be guiding you, is this value. It should not be exceeding that much. So to be able to do risk assessment, let me just add another page in here. It starts to get a little bit small. To do risk assessment, we need to talk about a few different things. And I'm going to be introducing some important terms as we talk about these 4 different parts. Part number 1 is going to be the hazard identification. Hazards, what are they? Well, it's going to be chemicals. And we call them pollutants because they are bad for our health or for the environment. And they could be not really giving any health effect, but they're still not natural to the environment, or they could be negative for your health or for our health. This is going to take us to 2 different things. One of them is going to be the dose response assessment, and that is going to be related to how much chemical is adverse for our health. So this is how much. We are intaking, similar to when you go to the doctor, they give you a dose, and it's similar to that. And then the second part is going to be exposure. How is this happening? Is it for everybody the same? Or maybe it's only for me because I'm the one that went to Denver for 2 months. So the exposure to the UV light was only for me or for the people that lives in Denver. So we're going to be talking about that. Is number 1, number 2, dose response assessment, and number 3 is the type of exposure. And then all of these together, all this data is going to be taking us to number 4, which is risk characterization. And the risk characterization is going to be actually calculating the risk, right? Determining the risk, a value. All of this is risk assessment. And whatever information we capture from here is going to be given to managers and go to risk management. So in the class, we're going to be concentrating more into the scientific data or information or facts. This is what we're going to be spending the time in the class. And with that, I'm going to end today's class. It's 3:45. But if you have questions, I'll stick around 5 more minutes. Otherwise, I will see you on Monday. Just remember that you need to have your notes for mass balance submitted this Saturday at noon and start working on your problems for the quiz next Wednesday.
Professor?
Yes.
Do we have, I'm just want to clarify. So we have our first reading notes is going to be for risk assessment?
The reading notes are for risk assessment, yes.
So we're not doing, there's no reading notes for mass balance and kinetics, right?
No.
Okay. All right. I'm just clarifying. Thank you.
Yes. No, and if for any reason you forget, I think it was Abraham asking.
Yeah.
Check off the agenda, and the agenda says starting risk assessment. Right?
Oh, okay. Got it. Thank you.
Yeah, no problem.
Is there anything above the risk assessment stuff you were writing? Yes,
Is it what?
Is there anything above the risk assessment that you were writing right now?
Oh, okay. No, that is the OneNote date.
Okay. All right, thank you.
No problem.
Professor?
Yes.
Where can we find the mass balance practice problems?
It's on Blackboard. If you look into the folder with the topic, mass balance.
Yeah, I found the submission, but I had trouble finding the problems themselves.
I was looking at those yesterday, but let me double check again. Because I actually updated and changed one of the problems. And maybe, I don't know, anything can happen. Mass balance.